Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks, Mike. So this is a pretty small group. I might be able to tailor my talk specifically to what you guys are interested in. If I know who you are, if you wouldn't mind telling me, are you guys from the systems groups or the AI groups or?
Programming languages.
Programming languages, okay.
The two of us, I'm Steve Luco, this is Dave Langford, he's from
Nice to meet you.
Java.
Oh, okay.
I'm Jim Laris, I'm from the software productivity tools.
Okay. Okay, great. So I'm Camille Whitehouse, and I'll be talking about declaratively programming a set of sensor network through what we call automatic service planning. So our problem scenario is slightly different from your standard sensor network scenario. We're going to assume sort of a fixed sensor infrastructure, meaning maybe a sensor network in the building or in the garage or something monitoring maybe a fixed infrastructure as opposed to an ad hocly deployed sensor network in a field. We're assuming that we have, say, a web interface to this network, and we're assuming a relatively high amount of processing in the network. So we're not talking about the extremely resource-constrained sensor networks like you might see in typical sensor network research. We're talking about maybe a building network where there are lots of sensors. It is a sensor network, but it's not typically your very highly constrained wireless ad hoc sensor network. Now, when you get this kind of sensor network, the problems become slightly different because we're not talking about conserving bandwidth or conserving power or conserving computation. Some of our bigger problems become, how do we interface with a common person? How does the common person program, 1,000 nodes to do the task that they want to do? We also have the problem of, well, if this sensor network happens to be running in the parking garage in our building or across our entire building, there might be dozens of people who want to run different tasks on the same sensor network simultaneously. And the resources in that network need to be automatically shared between the different applications. So our proposed solution is to run declarative queries over the sensor network. So we want to be able to say something like, I want a histogram of the speeds of cars in a certain area of the parking lot. And we want the query interpreter simply to give us that application. Now, declarative queries have a couple of different advantages. One is you don't have to do any programming. So this is automatically our interface to the common person. But there are a couple of other advantages as well. For example, you might be able to get goal-oriented failure messages. So if you pose a query and it can't be solved, the interpreter could give you a response such as, I can't solve this problem because you need extra sensors in this particular area, or you need to design a service that looks like this. Now, with imperative language, of course, you can't do that because you don't know what the programmer wants. With a declarative language, you know what they want, so you can give them goal-oriented failure messages. And furthermore, we can do automatic resource sharing with several different applications, between applications. And the reason is, if we take all of the declarative queries of all the users and put them together, that becomes one giant query, and we just try to solve all the queries simultaneously. We can also pose declarative constraints over our application. So for example, I want to be able to say, the confidence level of my car detections should be at least 90%. And the latency of the car detection should be no more than 5 seconds. This kind of constraint is useful because it allows me to put some sort of quantitative constraints on the application while allowing the query interpreter to make the appropriate trade-offs, not only within my own application, but between several applications that are competing for the same resources. Furthermore, if we have declarative constraints, we can do what's called execution monitoring and replanning. In other words, as I'm running the application, if I notice that I'm no longer satisfying the constraints of the user, you can simply replan, resolve the query, and redeploy. And that can hopefully all be done automatically. So the declarative infrastructure that I'm talking about is based on what we call service-based programming, very similar to what you might see in web service programming. So before I go into how we actually implemented a declarative language, I'll first talk about exactly what service-based programming means. So services are stateless, event-driven computational modules that have some clearly defined input and output. That's all that we're using the term service in a very loose way. And services can be composed simply by wiring them together. So the output of one service can go into the input of other services. And to get a concrete idea of what service programming means, let's go through a concrete example. I'll start with the sensors that we deployed in the parking garage earlier this summer. And this happens to be an application that we programmed using a service programming model. So in this particular case, down on the bottom you see the floor plan of the parking garage. This happens to be the down ramp. The cars usually go around. This is the up ramp, just for reference. Back there on the left, you see a stairway. That happens to be the 114, 115 stairway. And right around there, we deployed what you see here, 5 brake beam sensors. So this right here is a close-up of an infrared brake beam. This is basically your standard sensor bought at a Radio Shack and hooked up to a radio. So whenever the brake beam goes off, we send a radio message. That radio message can be received. We also have a camera, and we also have a magnetometer mode. And essentially what that is a magnetometer that can detect changes in magnetic field, also hooked up to a radio. And we have what we call a microserver, which is a receiving base station that has an Ethernet connection. So when it receives all the messages, it can forward them to whoever wants them. So what can you do with this kind of sensor network? You can imagine your standard user who has a PC with a web interface to this sensor network wants to write a program or wants to use it to do something. And the question is, how do they do that? And this particular user is what she wants is pictures of cars as they drive by, let's say, and a histogram of the times when cars drive by. So she has raw sensor data and she has a high-level goal. How does she get there? In this particular case, what she would do is look through her library of services and wire them together in an appropriate way that gives her the application she's looking for. So in this case here, what we have are brake beam sensors wiring into a brake beam service. The output of the brake beams can go into what we call an edge extractor service, and those go into an edge sorters that goes into a vehicle detector. So these are basically a bunch of different services. If you wire them up appropriately, you'll get a car detector. The output of the car detector goes into a report generator, and you can get both pictures and reports of cars driving by. Now what you would need to do to generate this is create what we call a MAML file, which is basically an XML file describing the entire service configuration. So the problem with this scenario is you need to generate this file. And what we're going to try and look at later is how might we generate this file automatically. But for now, I'll just give you a quick overview of how this actually worked. So the end result, which is actually a system that we actually deployed, as a car drives by the 5 brake beams, we get output of the brake beams up here. So as it drives by each one, you get an indicator saying it passed me as well, it passed me as well. This detects whether the thing is a car or whether it might be, say, an animal or a human or a bicycle. Which and all of this triggers the magnetometer, which starts sampling the ADC, measuring the magnetic field of the vehicle. If the car is big enough, according to magnetic signature, that will trigger the camera to take a picture of the car. And the output of the car detector also goes to this histogram generator. So I have a couple of videos to show. I don't think that they... Yeah.
Just a quick question. Are they sensors continually sending every so many seconds or milliseconds, or is it just when some changes occur?
They're event-driven. So usually they just sit there sleeping. When the IR brake beam, which is always running, basically signals a high voltage, which triggers an interrupt on the radio, which then sends a message. So let me just show a really quick image. Oh, looks like it went too fast. This is a video of a car driving by our brake beams. You can see the brake beams are back there on the right. As the car drives by, it triggers the brake beams. And since it's big enough, basically what it did is turn the magnetometer on at a delay, a slight delay, so that when the car drives by this position, which is where the magnetometer is, it'll get a magnetic signature of the vehicle. Now, on the other hand, we have also a video of a human walking by. Let me start this from the beginning again. As the human walks by the brake beams, you'll see that the signature in the brake beams looks very different. And in fact, this is easily discernible from a vehicle because these brakes are not overlapping, right? So obviously, this is a very short object, and it does not trigger the magnetometers. So we don't get a false positive when anything walks by. We actually can detect whether it's a vehicle or not.
Do the brake beams have a receiver on the other wall? Or are they just
They are transmitter receivers. They're only being used as transmitters, and the receiver is at the what's called the microserver, which is
yeah, like
a reflector.
Yeah, we have that. Okay.
A reflector, right? Not a receiver.
Okay. Oh,
sorry.
So that's all it has to do with reflector.
Yeah. And over the course of a day, for example, we might do things like traffic analysis, traffic pattern analysis, where here we can see how many cars drove by in any given time interval during the day. So you can see people stay until pretty late. Looks like they stay until at least 11. So that application was done, like I said, with service planning or service composition. And service composition, as we saw, is slightly easier than very, very low-level programming. So you don't have to write hardware drivers. You don't have to write distributed applications in your sensor network. You simply wire these services together. It also allows the reuse of other applications. So some of those services may or may not have come from other applications that somebody else wrote for the same network. And we can see that service-based programming is sophisticated enough, is powerful enough to capture what's necessary for at least relatively sophisticated applications, where in this case we had brake beams triggering a magnetometer, which triggers a vehicle, which also triggers a histogram. However, service composition is still, in a sense, imperative programming. It requires you to understand what the data is you're looking at, and it requires you to understand how the services are that you're using to interpret that data. Furthermore, because it's an imperative, in a sense, an imperative language, you can't get goal-oriented error messages. So when something goes wrong, you're the only one who knows why it went wrong. Furthermore, it won't allow the coexistence of multiple applications. So if somebody else decides to write a different application, we want to merge them. I have no idea really what the people want, and I have no idea how I might be able to take these services and mix them together or combine them and share resources between them in a way that doesn't is not counterproductive because I don't know what they're looking for. So what I'll be talking about for the rest of the talk is automatic service composition, which means, in this particular case, what's up here in the blue box. So our user on the left might pose a query. That query gets passed to a planner. And the planner can basically plan a service graph that will solve the query. That service graph then gets passed to what we call a generator, which is injected into the network and essentially deployed. And so once we get from this point to here, we're basically doing what we did in the first 6 weeks of my internship, which was generate a service graph, deploy it, watch it work on a sensor network. And what I'll be talking about from the rest of the talk is the rest of this blue box, which solves the query and generates a service graph. So the first thing we needed to do to generate this declarative language was a service markup language. So a very simple service markup that lets us, essentially allows us to get semantic meaning of the services. So the language is simple enough. We start out simply by declaring what sensors we have in the garage. And in this particular case, we have, let's say, a magnetometer sensor that measures this particular region. We have a camera that measures another particular region. And we have 3 brake beams that measure these 3 regions. Now, in this particular case, we're using a primitive, which is a cube, to define regions. And the cube is defined by 2 XYZ coordinates, which define the bottom and the top coordinates of the cube. This is somewhat limited because all cubes are in the same orientation, and we can't talk about sensing regions that are not necessarily in the same orientation. But for now, this is a very simple primitive to use, and as a proof of concept, shows us that the surface planner can reason about space. So after we define what sensors we have, we want to define what services we have. And this is a very simple markup language where basically what we do is define what the service is called, what it needs, and what it can create. So services in general create information. And for example, a brake service might need a brake beam sensor. And what it creates is an event X, which is a brake. And it also creates the fact that this event was detected at time t in a particular region. So a very simple sort of first-order logic type of markup language. Another sensor, for example, might be a mag service, which needs a magnetometer sensor and can provide you with a mag stream X. It'll tell you that this mag stream was detected at this time in this particular region. And it'll tell you what frequency it was generated with. And now there's another little markup right here called constrainable, which means that I can constrain the frequency to be whatever I want. Whereas I can't constrain, for example, the time. And now we use the same language for querying. So in this particular case, a query might look like car of X. So what I want is an event, which is a car. So this is a perfectly legitimate query. A more specific query might say, I want a car that was detected in this particular region. Or I might ask for a histogram of S, where S is the speed of a car, which was detected in a particular region. And the histogram of L, where L is the length of that car, and the histogram of T, where T is the time the car was detected. So you can see we can get sort of arbitrarily complex. The queries are essentially a very simple first-order logic, which is using the predicates that are defined in the service definitions. Now the question is, given these queries, how do we generate a graph that will solve that query? And what we want is something that looks like this. If the person asks for a histogram of the speed of a car, histogram of S should be resolved with a histogram service. Car of X should be resolved with a car service. Speed of X of S should be resolved by a speed service. And if we're lucky, the speed service, car service, and histogram service will be wired up something like this. But simply speaking, we don't necessarily know that, for example, the services aren't wired up like this. In other words, the speed service is detecting speed from these 2 sensors. The car service is detecting cars at those 2 sensors. And the histogram is detecting speeds at another 2 sensors altogether. In other words, we have an idea of causality where the speed is somehow the same speed as the event that's the car, and the histogram is really measuring the same speed, which is the speed of the car. Yeah.
So is it fair to say that the topology of services is only known by the services themselves, not by the scheduler?
The topology is, in fact, only known by the scheduler, not by the services. So the services really just get an input and an output, and they don't know anything about their surroundings any more than that. Whereas the scheduler or the planner is really the thing that's trying to assemble them.
Oh, okay.
So the question is, so our problem here is we want to generate a set of graphs, and we only want to choose those graphs that would satisfy this query in terms of the user's intuitive understanding of what it means to solve that query. In our case, we need to accommodate their understanding of causality. So we want the speed in the car to be the same. We want the histogram and the speed to be the same. Now, one way to solve this is essentially the way the user expresses their intuition on causality is by reusing the same variables. So because histogram is of S and the speed X is of S, we know that the speed that we're sensing here should be the same as the speed that's being measured in the histogram. Now, one way to enforce that is simply to munge the query a little bit. And when they pose the query, we simply put an ID on each of these variables. So the first S gets an ID of S1 ID, and the second S gets an ID of S2 ID. And then we require that S1 and S2 IDs are identical. We basically append this little, yes?
I don't understand why you can't. I don't understand why it's a problem. Why can't you figure that out from the query? Bring some assumptions to this that really aren't there. Why
Okay.
do you know that it's the same car? If you've got histogram, speed, car X, the speed X S is the correlation.
Good question. So let's see. And I didn't realize this, but implicit in this statement was an understanding of how this is all implemented, okay. Of course. And the real answer here.
So if there was a body of the Prolog statement and taken behind those two.
Oh, okay, right. So that's exactly the problem. That Prolog doesn't handle causality quite correctly if you were to run this in Prolog. Okay. Now, the reason why is what Prolog would do is something that looks like this. So when it tries to solve your histogram query, first it tries to prove histogram of S. And it'll do that by generating an entire tree, an entire proof, all the way down to the sensors.
Yes.
Then it'll try and prove your car query,
yes.
And it'll do the same thing. Basically, it'll replicate the end of that query over there. And then when it tries to prove your speed query, it'll do the same thing, replicating the bottom of these two queries. Now the problem is,
if you're running that as three separate queries, but if it's like the body of some one, then you'll tie those all together and you'll end up with a lot of backtracking. You don't want that tied together.
Imagine them as conjunct.
Yeah, so that's exactly what it is, conjunct. But yeah. Prolog solves conjunct by solving each predicate one at a time, right?
Well, I think it's dependent on the implementation of Prolog. Some of them.
Well, let's just go with vanilla Prolog.
Yeah.
If the unification of on the x's for the same.
That's right. So I guess another way to answer the same question is, when the variable is not instantiated, you can essentially bind it with anything.
Yes.
So let's say I had some other thing called speed of x comma s2.
Right.
This, sorry, it's also speed of x comma s, but there was a service down here called speed of x comma s2. Speed of s would bind with speed of x comma s2, whether or not that were the same as the speed that were generated from the histogram proof. I'm not sure if that makes sense. So when the variables are uninstantiated, they'll actually bind with anything.
Yes.
So we have no.
Say bound, but it's instantiated. Right?
That's right.
S hits in histogram.
That's right.
Bound.
That's right.
Then X hits, it's bound. Therefore, when you get into speed of X of S, those are already
Yes.
bound.
So let's say we go through the entire proof of histogram of S,
Yes.
never binding S.
Okay.
So S is simply a variable. We come over here. S is bound. We have another service where S is actually bound to something,
Okay.
Which is a different speed service than the one that was found by histogram of S. We may or may not find that service when we try to prove X speed.
So you have to go back and backtrack.
No, because what will simply happen is that the variable coming out of speed will be now all of a sudden bound to the same variable that was generated by this speed service over here. Because it was not bound before, so it doesn't actually. So you can bind it to whatever you want later on.
But isn't that what you want? Why is that not what you're So these are all different services, and one of them actually provides the speed.
That's right. Let me think of a good way to explain this.
So you've got multiple speed services.
So what we really want, and what the user is querying for, is this graph here, where they have a single speed service, and that speed service is somehow causally related to the car service and the histogram service. And the problem is, if we were to just simply naively run this query in Prolog, it would not necessarily give us this. And one reason is because what we really have is Prolog solving the query in a way that looks like this. And we have a very hard time identifying whether or not the speed services that are generated in these three proofs are in fact the same speed service or different speed services. Without some sort of identifying number, there's no way to identify them. And in fact, speed of s, or speed of x comma s, never has an identifying number because these two things are simply variables.
That doesn't make sense. I mean, in Prolog, the variables, the s, is what identifies all of the speed services and all the diagrams. They're all called the s, and then the unit histogram. So it's speed of s. It's one variable.
But
It would be the same speed service, the exact same result as the s.
That's actually not true. So, and I'm trying to figure out a way to explain why it's not true, why it doesn't work.
Do you want to just
Go ahead and read it.
Okay, we can do that. But beside the fact that Prolog wouldn't give us the solution we were looking, wouldn't constrain us to only the solution we're looking for, it also wouldn't give us all possible solutions that we are looking for. So, for example, if we have two sensors S1 and S2, which are generating events X1 and S2, and we want to be generating a third event called X3, where we have speed of X3 and a length of X3, we have no way of knowing that the speed of X3 is the same as the length of X3. Right? So basically what we're doing here, we have no way of binding the value of X3 and X3 over here and X3 over there, because they're never put in the same conjunct anywhere. What we really want is to be able to say X3 is the same as X3. This X over here is the same as that X over there, if they're fundamentally reliant on the same data. And the problem I was explaining before was something like this, where if there's a conjunct, a query at the bottom, a precondition of car, which is a conjunct requiring speed and length, any variables that come up from speed, the result of the speed query are basically bound to the variables in the length query via the query. And what we really want to do is have the query asking if the variables are the same. Sorry, this is slightly confusing here. So let me move on a little bit. So, like I said, what we're doing here is munging our queries and munging our services, so that the query is adding a query predicate called is identical, and each service is positing a new clause which says these are identical.
And is it a user who writes that down, or?
So this is all done automatically. This is part of the query processing. So the user would simply pose that query up at top, and the query processor will change it into a query that looks like this. And as the user defines a service that looks like this, the query processor will redefine it into something that looks like that.
And what is this one you identify? A speed service?
So in our particular case, let's see. Yes, that's exactly right. It identifies a speed service.
So you're saying that speed services are facts and existential
Rules, yeah.
It's sort of it's a fact. It's like a fact. So you have multiple speed rules. You're saying which one you get. Making sure that both sides hit on the same speed rule.
Yeah, that's, well, so let's say we only have one speed rule, but we could have multiple instances of speed services. Right, so the user defines a service called speed.
Yeah, so that instance of a speed service is a fact, right? You have something speed, it's ground. It's a ground fact.
No, so there is no fact called a speed service. The speed service is a rule which says if I have these if I have, say, these sensors, I can generate speed.
So it's a answer. Okay, now I understand what you're saying.
So the speed service is turned into a rule that says, if you want speed, you need to prove these other things, which are the prerequisites to having a speed service, which in particular might be a certain couple of sensors.
So S1 ID is sort of an identifier for a proof term?
That's right.
So
In a sense,
grounded
that's right.
instance of speed.
That's right. The grounded instance of speed, exactly.
So you have the same grounded instance of speed that you pass through, so you're sort of turning down.
That's right. That's right. So as you run through the proofs of each predicate in your conjunctive query, you want to make sure that you're using the same, essentially the same ground instance of the same service. Whereas it might be that, for example, the solution to this predicate uses a speed service based on data over there. The solution to this predicate is also possible, but it will have to use a speed service based on sensor data over there. And there's not really any way. Prolog will not prevent that. So
I think what was confusing us was there's this implicit notion that the rule speed is a generator of instances. But like we were thinking of it as just, okay, that's the service that's going to play in there. It's a fact. Right? If you just said every time you prove that rule, you generate a unique instance of service speed, and therefore I need to label them so that I can make sure that the instances involved in the two proofs are the same. That would help me.
I see. So is it clear now?
Yes.
So what up?
SMS.
So I guess I hope that's clear now. But
You're good. It's fine.
okay, what you said is not exactly correct, though. I just want to make sure that this is clear. When you do essentially apply a certain the speed rule, for example, you generate a speed service. Uh-oh, what's going on? Okay. You generate a speed service essentially, but it's not necessarily a new unique speed service every time.
But there's a set of speed services that you can get from your sensors.
That's right.
Right. You have to pick one.
Right.
And put that one through. So maybe it's not a new unique one. You've got this sort of instantiated, this new possible integrators.
Right.
Services.
Right.
You have to make sure that the speed service you use in histogram is the same when you use somewhere else.
Right. Right.
Right.
That's exactly the problem. Exactly the problem. Okay. So we have causality problems. We also have uniqueness problems, and I think I've already gone over the uniqueness problems, which are essentially what we were just talking about. And the way we solve the uniqueness problems are by munging the query again. So when we query for something like a car service, we first check to see if a car service already exists, and if it does, we check to see if that is a solution for our query. And if it doesn't exist or if it doesn't solve our solution, we generate a new car service. And we munge the service definitions so that when we apply this particular rule, what we do is we create a unique instance and we say this instance exists so that we can query it later on. Yeah, that's right. But this is actually not quite Prolog notation. What that really would be is, that semicolon is essentially or. So what we want to do is see if, looks like I missed a parenthesis there. So what it should really say is either look for either a car service already exists and that solves my query, or generate a new car service. Apply the rule again and generate a new car service. So what we really want to happen is, as we prove the first predicate, which is histogram, we generate a proof that looks like this, and instances of services are generated along that proof. And as we prove the next predicate, it'll reuse the same instances. So as opposed to forming independent trees, it'll basically reuse the same instances if possible. Now that same mechanism allows us to run simultaneous queries. So let's say that our user simply poses a query that looks like this. I want a histogram of S, where S is the speed of something. I just want speeds in general. And now another user poses a query that says car of S, or car of X. So that's a typo. Car of S should generate a new car instance, and that car instance reuses another service, a speed service instance, which was generated by somebody else's query. So the same mechanism that we have of essentially services instantiation and querying for existing services before we generate new services allows us to run simultaneous queries. And now when a user finishes his query or deletes his query, there's a very simple mechanism for deleting services without destroying somebody else's query. So instead of deleting all the services that he instantiated, all we do is delete services one by one that have no successor node. So in this particular case, we delete histogram because it has no successor node because the original query was gone. But we don't delete speed because it does have successor nodes. So we can have multiple users posing queries at different times, deleting the queries at different times, and having the service graph be complete and consistent. So now what I'll talk about is applying constraints. And this is a pretty significant part of this declarative language. So as you probably know, in Prolog, the statement x is greater than 2 is a Boolean statement. It's either true or false. And what it's really saying is there some x such that x is greater than 2. And so, for example, we might have service x, comma x, where x is greater than 100 and where x is less than 100 be true in both cases. And what we're using is constraint logic programming in addition to Prolog, where the statement x is greater than 2 is true if this particular constraint is consistent with a constraint database that we have. So I might have other constraints on the same variable x, and if x is greater than 2 is consistent with those, this statement will evaluate to be true, and it will add x is greater than 2 to our constraint database. So then subsequent queries such as x equals 2 or x is less than 2 will result in a false. The other important thing to know about constraint logic programming like this is when the program returns, we will have a bunch of residual constraints, so constraints on variables that have never been instantiated. And we can actually extract those from the constraint database. So in this particular case, when we return, we'll have the constraint x is greater than 2. So I'm going to show how we use these kind of constraints in our query interpreter. So we might add, for example, we might have a query, for example, I want a car, the speed of the car should be greater than 30 miles per hour. So basically what I'm querying for is all cars, what the user thinks he's querying for is all cars where the speed is greater than 30.
So is this querying from some point back in time to the present?
In fact, it's querying from this point in time into the future. So there are declarative languages that will query about data in the past, and I guess SQL would be one of those. So you have a bunch of data and you want to query over that data. What we're doing here is slightly different. We're querying over data in the future. So give me all events that satisfy the query. X is a car, and the speed of S is greater than 30. And I'm querying over all events that might happen in the future.
Does the query ever expire or time out?
There is currently no way of timing them out, but
It's not really just a predicate that you can apply over
right. But it would, yes, exactly.
This is independent of the stream of data. If you had a log, you just ran this over it, and then you get historical data for each one, just hooks it up to a lot of sensors, gets it right back. That's what happens.
Right. So what I could do is add a predicate here that would say X was detected at some time t. T is less than 2,000. So that would essentially expire your query, although your query would still be running there looking for more data where t is less than 2,000, but that would solve that problem. So after I pose this query, I generate a service graph, and I have a couple of residual constraints, such as x is greater than 30. Now I take those constraints and I have passed them to all my instantiated services. some services, such as the speed service, for example, would be able to take that constraint and take it as a parameter. So the speed service would say, okay, well, the user is querying for s greater than 30, so I will not generate any speed events where s is less than 30. And so what that would do in our high-level graph is the speed service would not generate any speeds where s is less than 30. The car sensor would never get those speeds and never detect cars either. So I'm essentially querying for speeds that are less than, or cars with speeds greater than 30. You can similarly apply these kind of constraints to quality of service values. So for example, if I want cars where the confidence of my car detection is C, I can require that C is greater than 0.95. And services can propagate these constraints. So for example, if I have a car detector with confidence greater than C, or the confidence C, and this car detector the car detection is based on the speed of an event and the length of an event, and those two values have confidence levels. I might define C to be C1 times C2. So in other words, the confidence of my car detection is the product of my length confidence and my speed confidence. Oh, I guess that should be C2. Yeah. And now what's going to happen if I pose that query is that C greater than 0.95 is added to the constraint database. This is added to the constraint database. And as these variables are passed into the rules to instantiate these services, essentially what you're going to have is a relationship between the confidence levels of speed and length. So if, for example, speed all of a sudden binds its confidence to a specific value, let's say 0.8, then we can fail the query because we know that 0.8 times anything is not going to give us a number greater than 0.95. So immediately, so when this applies the constraint that says C1 equals 0.8, that particular constraint will fail, and the entire query will fail.
Well, Phil, I mean, if the sensor had a confidence, well, yeah, it does. So could the sensor fail it, or does it have to go up to the query process? Could the sensor just not send it? I mean, would you try and push that information down the sensor saying you have to be at least 0.95?
Okay, so in this particular case, what I was talking about is where the speed service knows its own confidence level. So it happens to know in the rule that...
I meant to say at the speed service level.
Right, so the speed rule happens to know that its confidence level is 0.8. Now let's say that it didn't know that its confidence level is 0.8. We would end up with a bunch of residual constraints on all of our confidence levels. And these residual constraints can be passed into the services as parameters. And at runtime, so at execution time, if the confidence level falls below this, or violates these constraints, then we fail at execution time. So there's a difference between failing at sort of compile time or planning time and failing at execution time. But there are mechanisms for solving either one of those problems. This is pretty much exactly what I was just saying. Let's say that we don't bind our confidence levels to any particular value. These residual constraints can be passed as parameters to the services. So the service would get a parameter that says, for example, my confidence level needs to be greater than 0.8, greater than 0.95.
What's the model by which those parameters are established?
I'm sorry.
Do you mean that the runtime group around the service knows about parameters based on constraints? Or like parameter sounds like the thing is a function and you're adding arguments to the function.
That's right.
Which I can understand doing under the covers, but there's no programmer model there, right? When you say parameters, you just mean under the covers I'm adding an argument to this function and then I'm passing it, and basically all services have some infrastructure
That's right.
that understands how to propagate constraints.
They will basically take a set of constraints and interpret which ones are important to them. So it is very much an under-the-covers thing. Essentially, each variable would get a set of constraints. C1 is greater than 0.8. C2 is greater than 0.7. C3 is greater than 0.9. It will happen to, let's say, we can even just pass it in as a string. It'll have to parse these and figure out which constraints are applicable to it and which ones it wants to apply in what way. So yeah, it is very much under the covers thing.
It confused me because when you first started talking, you were describing the services as induced from this declarative description. And so I got this idea that the person who wrote the declarative description might see a graph of the services, and then that they might be parameterized by things, and that might be part of the features of the induced services that the person saw. But really what you're saying is the person who wrote the declarative query does not see any such thing, but that there's potentially a base class of service infrastructure that all services inherit that take you the parameters.
That's right. So the user wouldn't see any of this happening. This would all be done by the query processor and the deploying engine. And yeah, all services would need to have some sort of superclass that takes a set of constraints. And if they chose to, they could override that function and implement a certain set of those constraints, or simply ignore all of them. That's right.
So are you saying that if there's a explicit model of specifying the program?
No, I was just trying to get a sense of what semantics of services are exposed to the programmer and what aren't, and why. Like, so far it seems like the programmer doesn't even think about services. They just think about expression.
That's right.
I guess there are two kinds of
Programmers. There's one that writes the service, and there's one that poses the query. So I guess there's the programmer and there's the user. And I guess the programmer does need to think about these kind of things, and the user does not. They may or may not be the same person.
So if you have multiple queries, do the constraints get combined in an intelligent way? Like one guy wants only speed over 20, and one guy wants speed over 30. You always have to tell the sensor speed over 20.
Very good question. And that's exactly what I was about to talk about. So I guess the question is, how do we combine constraints? There are limitations to constraints, and in particular, limitations with our first-order logic query language. So in our particular case, we want lengths of cars, and we want those lengths. We want car events where the length of the car is greater than 30. Does this query ask for that? No, it doesn't. Or at least in our case, not really. So what we solve the first part of that query with a service graph that looks like this. We posit that L is greater than 30, and that constraint is passed to the length service. So the length service only generates lengths that are greater than 30, but the car service generates cars for all cars, whether or not the length is greater than 30. And if we wanted to actually satisfy that query, we would require that car is actually dependent on the output of length. But there are problems to this as well. So let's say I wanted a histogram of lengths, and I put a constraint on my speeds. In this particular case, we want speeds of cars, or we want cars where the speed is greater than 30, and we want a histogram of all lengths, let's say. This query is simply not solvable in the way that the user wants. So in our particular case, what we're going to get is all cars where the speed is greater than 30, and a histogram of lengths where the speed is greater than 30. And the problem is, our constraint S is greater than 30 is simply a global constraint. What we really want to do, what the user really wants to do is sort of parenthesize the first three predicates and say, this constraint should really only apply to these two predicates. But in first-order logic, there's not really any way to do that. You simply posit, this is the constraint. It applies to all other predicates, or it applies globally in all other predicates. You need to accommodate that. So the only way to solve that kind of problem is essentially to pose two queries, one with the first three constraints, one with the second two constraints, and have them run independently. So the limitations of first-order logic, I guess, are that we can't necessarily apply the constraints to a certain subset of things, even though it might appear here that we are doing that. In fact, we're not. One important reason for using constraint logic programming is that our query processor needs to reason about space. So in general, people have taken web services, for example, and composed them using partial order planning or some other sort of planning mechanisms. And the problem is partial order planning and other planning mechanisms cannot do any reasoning. They can only do planning. In our particular case, we want to do planning and reasoning at the same time. So we want to say, I want to plan this particular service. And it requires a certain set of sensors, and those sensors need to follow these constraints. In other words, these sensors need to be in this particular region, or these sensors need to have certain quality of service values. So in our case, we need to do planning and reasoning at the same time. And this is what we use constraint logic programming for. So we can define predicates such as this subregion is a subregion of that region, or region 1 intersection is the region intersection between region 1 and region 2, where regions are, like I said, cubes defined by two three-dimensional points. And I can also say union is the union of region 1 and region 2. And then when I pose a query, I can pose a query such as this, that I want cars X, where the region, oh, sorry, there's a typo here. That should really say subregion. So where region is a subregion of this, and the car was detected in that subregion. And so what this constraint here, what this rule here does, is basically apply a bunch of constraints to the XYZ coordinates of region. It returns some variable called region, which has a bunch of constraints applied to it. Those constraints then get passed down into this detected predicate. And whatever variables region is bound to in the detected predicate must satisfy those constraints, and if they don't, the predicate will fail. So essentially what we're doing here is generating constraints, passing them down into the predicate, into the proof of the predicate. Constraints can also help us do resource sharing. So for example, I might have a sensor which runs at some particular frequency f. And as so the preconditions of this particular sensor are that the frequency needs to be less than 400 hertz, let's say. And we have and I threw in this little clause that says minimize f, and you'll see why in a second. Let's say I have another service that uses that sensor. So it uses it, and it calls this frequency f1. And this service also provides a frequency. And it requires that that f1 is some multiple of this frequency. Right? So essentially what it's doing is downsampling the frequency of this sensor. So what we're doing here is saying frequency f needs to be essentially the frequency of this sensor divided by some number n, where n is an integer. Now if I pose a query that looks like this, let's say I generate two of these streams, each running at a different frequency, what we're going to get is the constraint that f1 is 5 times some integer, and f up here is 5 times some integer, and f is also 12 times some integer. And so what we'll do is generate f to be something like 60. So the frequency of the sensor is going to be 60 hertz, and that satisfies both of these queries. And actually, all we're really saying is f needs to be either 60 or 120 or 180 or something that is an integer multiple of these two numbers. And thus, we put this constraint up here called minimize f, where minimize is simply a function that at the end of the entire query will choose f to be the smallest number possible, which will be 60. So now we have two users, each of which is using the same sensor at different frequencies. And this can be solved using constraint logic programming. So essentially, it'll bind the frequency variable on the sensor to a specific number that actually solves both queries.
What if they couldn't be solved? What if there wasn't a frequency that solved the problem?
It would fail.
So do you have any notion of, like, they both fail if they're separate queries, or can you give one priority?
I guess in this particular case, it would be first come, first served. So if you happen to pose a single query with inconsistent constraints on a single sensor frequency, it would fail. If you pose two queries, one first and another one second, the first one would pass, the second one would fail. one important aspect, like I said, of this query processor is that it can do inference. So there's a lot of planning algorithms that do service composition. In our case, we're not really doing any planning. What we're really doing is taking a planning problem and turning it into an inference problem by changing our service definitions into rules and running inference over them. And what this allows us to do is infer preconditions of services. So, for example, this is one of the service definitions in our service graph. It requires what's called a break group, which returns a group in some predefined region. And it says the length of the group has to be greater than or equal to 2. And there are no intersecting regions of the break beam, the break services in this group. Now, break group itself is a rule, and it happens to be a recursive rule that will essentially continually add on new break services. So what this will do is essentially try a single break service, see if that passes. That'll fail. It'll backtrack, add a second break service. That'll pass here. If those two break services have intersecting regions, it'll fail here. It'll backtrack, add a different service, and it'll keep on doing that until it has a set of break services that fulfill all constraints. And so essentially what we're doing here is allowing an undefined or not predetermined set of input parameters. So this particular service can take 2 break beams as input, it can take 3 as input, it can take 4 as input, etc. And this is the kind of thing that you really need to do in a sensor network, where services can be defined over any set of sensors, but which you can't do in, say, partial order planning, where you would basically need to, in the preconditions of the action, define I want a break beam here, a break beam there, and a break beam there. So I would need to define this service needs 3 break beams. There would be no way to define a service that requires an undetermined number of break beams, for example. Like I said, because we're using declarative languages, what we should be able to do is say something like, your query failed because you need a sensor X. Now, this is actually a very difficult thing to do, and I have not done it yet, but it should be possible. And the way I think it's possible is, as you solve the predicates in the query, you'll fail at some point, and the remaining part of the query should be the part that is not solvable. Now the problem is, because you're backtracking, you're trying many different solutions, you can't just choose a single failure point. You can't say, oh, I failed at looking for sensor X, because it actually tried 10,000 different ways of proving the query, and you don't know which one of those failures was the critical one, or was the one that was easy to solve. Another way to do this would be to change our munging of the query into something like, if I want the service car of X, I can either look to see if the service car of X exists, I can instantiate the service car of X, or I can pretend I instantiated the service car of X. And what I'll do in that case is, when the query finishes, I'll basically take all the services that I pretended I solved and say these are the services you need. So this is an unimplemented feature, but because we have a declarative language, we should be able to give goal-oriented meaning, goal-oriented failure messages. A couple of related projects. One in particular called Sword does a very similar thing. It takes service definitions, changes them into rules, and then runs inference over them. There are several differences between this and Sword. Number one, Sword has a very limited query language. So the only query that you can pose is the exact preconditions of a single service. So I pose the preconditions of this service. It tries to prove that service, and it'll prove it by adding any other services it needs. You can't add essentially post conditions of multiple different services and have them causally related in the correct way. Furthermore, it can only find tree structured because it's an inference engine. It can only find tree structured solutions, so it can't find arbitrary directed graphs. And it cannot reuse services between. For the same reason, it cannot use services reuse services between queries. There's another solution, another project called essentially planning using SHA-2, which is a hierarchical planner. This, just like the other partial order planning solutions, cannot use inference. Inference rules, it can only do planning, so can't do any reasoning about space or time. And SHA-2 also uses, in a sense, an imperative language in the sense that with a hierarchical planner, what you really do is pass in the highest level plan and say, somehow prove this plan by decomposing it into elementary parts. But still, the user needs to know what needs to happen. So it needs to know this needs to happen first, this needs to happen second, this needs to happen third. Now show me the actions that can solve those high-level actions. And because it's in a sense an imperative language, when it fails, it won't really know why it's failing. So before I go to the quick demo, let me conclude by saying service-based programming helps program sensor networks because it's easier than low-level programming. It allows the reuse of services from several different applications. And it's powerful enough to capture several different applications, including sophisticated applications. Now, when we add automatic service composition is slightly more powerful in that it allows you to do declarative programming. It allows you to make constraint-based trade-offs. It allows you to do execution monitoring and replanning. It allows the coexistence of applications. And it'll automatically do resource sharing and reuse of resources between different queries. So let me give you a quick demo of the query processor. And I have to say the implementation implements most of the features you saw. Some things like meaningful error messages are not implemented. And there is a particular bug which I hope not to hit and I haven't had time to solve. It's very easy to write programs in Prolog that run forever. And there is one of those in my program and I haven't found it yet. So if it runs forever, that might be a problem. It'll either solve in about 1/10 of a second, or it'll run forever. So I'll show you quickly the service definitions that I'm using. So I have a bunch of sensors over here, defined over there, a bunch of objects as well, which I just threw in there for display, and several services like a brake service. I have a triggerable mag service, which is a service that will basically read from the magnetometer based on an event. I have a triggerable photo service, direction service that will basically take brake beam information and tell you which direction the car is moving in. Speed service, length service, car detector, human detector, and a couple of histograms. And then again, I have a couple of helper functions like these region intersection definitions. Down at the bottom, subregion, region union, and at the top I have a break group definition, which is a recursive definition that will continually add break beams until it solves the query. So what I'm going to do is load that file. And I haven't actually run this on this laptop before, so let's hope it works. And when I loaded the file, what I see here is the sensor regions and the objects in the room. So this happens to be the parking garage. These pillars are the pillars between the cars in the parking garage, and this big gray thing in the back is the back wall. And this is very similar to the video we were just looking at. If I put it in that orientation, this is kind of the way we're looking at the video before. The camera was right here, and the cars were driving down like that, and there were brake beams. Oh, sorry, or on this side of the pillars. The camera was right here. The cars are driving between the pillars and the wall. So this is a sort of a virtual reenactment of the situation we had on camera. And what I can do is, let's say there are a couple of features I want to demonstrate here. So, for example, let's say I wanted to detect direction. Let's say direction can be solved with only 2 break beams. When I submit my query, I get a task graph showing it can be solved with only 2 break beams. And if I want to solve for a car, the car requires 3 break beams, so it generates this other graph. And I can see I have 2 queries coexisting with each other. All right, I guess you got. Yeah.
We got a couple of questions on the meeting.
Okay.
Do you have this is very interesting. Thank you very much.
Sure.
Do you have any more time? Do you have any time before you leave?
I do. I'm leaving tomorrow, but I have time today and tomorrow.
Okay. So do you need it?
Okay, great. Sure. So what you see here is my first query, query 1, which was solved by a direction service, which used 2 break beam services. My query 2, which was now called query 13, which solves for a car detector service based on what we have here is 3 break beam services. And now if I were to, and you'll notice that query 13 instantiated a new direction service, because the direction service is actually different from this ground instance of that direction service because it uses different sensors. But it reused these 2 break services because these 2 break services can be shared between this query and that query. And if I were to, let's say, remove query 1, it'll remove only the services that were only dependent, that only query 1 was dependent on, and it won't remove the services that, say, query 13 was dependent on. I'll remove query 13 as well. And let me show you quickly that I happen to have defined here 2, let's see, where is it? 2 length services. So these 2 services right here, where in one case, this service requires a break group with at least 3 members. This one requires a break group with at least 5 members. Now this length service, because it only has a couple of sensors, let's say it can only detect lengths that are less than 30. Whereas this service here can detect lengths that are less than 50. So that it'll never output a length greater than 50. But it requires 5 break services. So now if I were to pose a query length, that query would be solved with a length service dependent on 3 break services. And now instead, if I were to pose a query, let's say I wanted the length to be, I wanted to use make a query of lengths greater than 30. Whoops, sorry. I basically typed in constraint L is greater than 30, and I want length. I want length where L is greater than 30. I can no longer solve that query with the service graph that I just showed you, because it only has 3 break services and it can't detect any length greater than 30. So what this will do is generate a length service based on, say, 5 break services. So it'll use the second definition of the length service, where it requires more break services but can give you longer lengths. And now let's say I want to detect a car service. My new query, which is 85, will reuse all of these services. And just as a quick demonstration to replicate the demo that we did down in the garage, let's say we want a mag stream, and we want that mag stream to be triggered by the car service. So we have a mag stream which is triggered by a car service, where a car is defined to be Y. And now I have a new query, 87, which is dependent on my car detector, and is dependent on this triggerable mag service, where the triggerable mag service gets triggered by the direction service. So the direction service is the first place that instantiates the object that's later to be determined to be X. And what this does is read from the magnetometer when we get a direction event. And finally, what I want is a photo service where photo is triggered by the mag stream Y. And let's say I only want that to happen for big cars. So I only want to take pictures of big heavy metal cars. So I want the intensity of the mag stream Y to be greater than 100. I submit that query, and my new query over here has a triggerable photo service, which is triggered by the mag service. And we have a constraint that this mag service is only outputs intensity is greater than 100. So now essentially what we have is a replication of the original demo that we did down in the parking garage, where we have the service graph sitting sort of on top of our sensors. But instead of composing it by hand, we simply posed a query, and that query was automatically solved. I think those are all the features I want to demonstrate. So that's it. Thanks.
So in examples you have, the sharing of these services quite unique. In case where there's not always shared services, what would you actually use to constrain which way that you want to use the sharing of the service?
I'm not sure what you mean by multiple ways you can share services.
So for example, you added a calculation.
Yeah.
The calculation provide the services and using the 5 sensors. The car that you can also use maybe some sort of
Right.
car.
Right.
Except that it's already computing an answer and so on. So you still
Okay.
deliver
Yes.
the cost. So there's some notion about how you wire them.
That's right.
That's the one goal.
Yeah, there is. So like I said, the query processor, basically what it will do is when it tries to solve the preconditions of the car detector, it'll look for either a length service that already exists and solves this query, or it'll generate a new length service. So in this case, it has a length service. The length service satisfies the query. And so it does reuse it. Now let's say that when I pose my car query, I posed it over a particular region. So I amended it to be over a particular region. And whatever that region might be is inconsistent with the region that this length service is over. Then it'll try to use the existing service. It'll fail. It'll regenerate a new service that does satisfy that region. In this particular case, I think this is the right thing to do, because if the length service is running anyway, it's not any more efficient to only use 3 break beams. It's just as efficient because it's running anyway, so we might as well use it. But if that length service, so even if the length service is overkill, it does satisfy our query, so we might as well use it. If it didn't satisfy the query, we would generate a new one. Yeah.
So does mag stream sort of imply that it's continuous data? You just had a query mag stream of X.
So what mag stream gives you is a mag stream of X, which is, in this particular case, a set of data points with a certain frequency with a certain duration. So it might satisfy it at 10 hertz for 3 seconds.
I guess my broader question is, how do you request continuous data? Like, you want to read the temperature continually.
Oh, continually.
For the next 10 seconds.
So what we have is a triggerable mag service, which means it's required to be triggered by something. Now, we can also have a standard mag service, which simply gives you mag data. In that case, instead of using a triggerable mag service, we would just use a mag service.
How often does that get sent, or how do you control how often that gets sent? Or is it just a parameter?
Right. It would just be a parameter. So the mag service would generate, let's say, several different predicates. One is called mag stream of X. The other would say the frequency of X is F. The other one would say the duration of X is D, etc. And you can basically set constraints. I want a mag stream of X where the duration is D, and D is less than 100 seconds. Right, so that's the way you oppose that kind of query.
Okay, thanks. Cool.
Thanks, Kenny.
Sure.
Are you guys good with this? Let's see. I think we got the crossroad.
Okay, we're going to come back to talk to you about you want to show like the current day stuff with the crossroad. Hi, Roland Fernandez. Hi, Jeremy Nelson. Hi. Okay. Yeah. Yeah. What do you introduce yourself?
What do you order from Costco?
We ordered their sampler kit, which is like 12 sensors and such. The MOTET.
The magazine?
I don't remember. Some other guy ordered. I looked at it a week ago. It was like yeah, we were looking at that, and we were looking at the finally decided we wanted the flexibility of being able to set a couple more if we wanted, and being able to break it open.
Right.
Being able to demo the system, of course. Yeah.
Great. Yeah. That's really good.
I'm glad I like their work.
Yeah.
So what was that? Where did that GUI come from? You did a 3D visualization GUI?
Yeah, no.
Oh, okay.
Pretty cool, yeah.
Is that a lot of codes that you rendered out?
In the past 2 days, the code is loaded to about 8 I think still nothing on the line. No, so I think that 3D visualization code.
Well, what was it? Was that whole window that one? Or just the
whole window. So yeah, before the 3D version, or the 2D draft, and that whole thing took maybe like 2.5 to 3 hours to do it. And that was just so easy to write visuals with buttons and I even had to learn how to use a GUI in that. Learn how to do it and did it in less than 2 hours.
See the code on the network somewhere?
We're going to go over that.
So how does it know what's the action iteration? Is it placement? So you just get edges and it figures out where to place them through and know
that was actually a little bit more difficult. Basically, you can just give it, let's say, a tree, and it'll plot a tree. If you get a drag and graph, it won't know how to plot a drag and graph. What I have to do is run the drag and graph into a tree in the appropriate way. It will generate a tree, and then I can do the job.
So the render, you will go on the render.
I used some of the rendering of myself. I'm not sure. I didn't actually do any pixel thing. There are a couple functions like fill with the draw, fill box.
Yeah, no, but I see when you add another query, right? The previous one,
Oh yeah. So all I did was when I removed the query, there's a bunch of data structures.
Something.
I think it's anything that
It's
covers
scanning. I don't know. I don't know whether it's recorded in that.
So how does it, so when the two queries that are sort of jutting out from the same thing, you remove one and one goes to the right side. It's pretty much because the query is stored in some big matrix. There's a matrix that has edges. You delete the queries, you remove things from the matrix, and you redraw it back to the scratch. And then that's how we draw single query query.
So, okay, so you're going to document some of this stuff. I mean, wouldn't it be nice to do like a high level logical diagram how you can piece it together? Even though you have to you're using is basically you have the Prolog implementing plus the logic constraint solver together. So what will be the logic steps involved in the proof of this when we get there and satisfy?
What if you don't have that Prolog?
So we didn't have it.
Right. Independent of a particular tool you use, what will be the logic of the steps you have? So in other words, if someone wants to implement not Prolog, some other tools, what will be the steps you do? Also, Prolog is kind of the travel version, so I think we can write it down.
The demo new kind of
Oh, right.
They just use Microsoft Logic Blaster 2000.
Is it something like that?
No,
That's what you're going to learn.
Actually, it's unfortunate, but this code probably was one of the Prolog ever decided on.
Oh, really?
There are.
What's the one that's unique to this? You turn off the
Yeah, turn that microphone off.
mic on.
It's the constraint logic program.
I see.
So, constraint logic program is not really a language, it's a library. And Fixit has their own library and Satisfies their own library. So the syntax actually it's like
I see.
it would be pretty easy to just go through and change the syntax and it would work. But then there are also different versions of Prolog. Like ISO is actually what I'm running, but a lot of other interpreters don't run ISO. They run this proprietary modification of Prolog. So there are a couple that I'll run on the standard in which case it should be easier to do things. I tried about 5 different Prolog interpreters, and this is one more than probably did it.
Have you got Edwards?
No. Is it about you?
No.
I haven't.
Okay. I'll get back. 3:30.
Do you have something next week?
There's a talk I was going to get to.
I need the work stuff.
Radio Common, something in the talk, I think.
That's amenable.
That was the same one.
I think that's what I need to work with. Yeah.
Yeah, that's something really right.
You use the protocol sheet.
Yeah.
Yeah, I've done that.
Well, whatever you pick up time.
What time?
He said he's free. He's free today except 2 to 3:30. And then tomorrow.
What time are you?
Probably 3:30.
Because you have all right. We're very happy. Yeah.
Yeah, that's right.
Right. Those guys are really actually into the details.
Yeah, there was that one part I was hoping to sort of wave my hands over because it's a really hard part to explain.
You mean the binding of
Why a simple naive Prolog query won't work? Hard to explain, but I'm hoping that nobody uses Prolog and nobody has to.
That might work.
Yeah, it doesn't. So, I think they might have gotten that.
all right. Do you want to grab some lunch or?
Yeah.
So the guy who's sitting here, his name is Rowan. They actually can give you some interesting histogram.
Is he further this way?
No, he's not part of MSI. He works for the CTO of MSI. And they try to do something more along the line of envisionment. Like the home, right?
Oh,
it was actually part of that organization but they spun it off to some party. And but they actually interestingly, the thing actually, in the sense of language actually has it's going to actually have some impact on including so on. So they want to actually do something like that. So I think in some sense, LBR, that's a sense for the LBR 3D aging stuff. Advertising this. And then they probably will get hard questions about how this works. All right.
Yeah, you would have liked, I think, that Microsoft phone towards the back yesterday.
Yeah.
You really missed.
Yeah. That's good.
I mean, yeah, it's a
very simple
house.
layer.
I mean, they sort of are on the line of it's sort of a fake demo and sort of not. Like, so like you walk up and yeah. You walk up to the outside of the house. They have a little